Hello everyone, welcome to NGI's Technical Podcast. My name is Zhongqiang Liu. I'm a principal researcher at NGI. Today's honorable podcast guest is Professor Kenichi Soga. On March 19th, Kenichi delivered the prestigious Rankine lecture in London, one of the highest honors in a geotechnical field. After his Rankine lecture, he traveled to Oslo and visited us at NGI. Kenichi is currently the Daniel McLaughlin Chair and a distinguished professor at the University of Berkeley, California, and the director of the Berkeley Center for Smart Infrastructure. He has explored the use of data and sensing technologies to monitor infrastructure performance at the University of Cambridge and the University of California, Berkeley. At Cambridge, he played a key role in the establishment of the Center for Smart Infrastructure and Construction, CSIC, which has driven advances in computer vision, fiber optic technology, and wireless sensor networks for infrastructure monitoring. His research in the University of California, Berkeley spans diverse areas such as infrastructure sensing, performance-based design, maintenance of underground structures, engineering geotechnics, and geotechnics from the micro to macro scale. He has 40 years experience, has published more than 500 journal and conference papers, and is the co-author of Fundamentals of Soil Behavior with the late Professor James K. Michael. The new edition will appear this summer, and Professor Catherine O'Sullivan of Imperial College is a newly added co-author. Hi Kenichi, welcome to NGI again after quite some years since your visit last time. And it's great to have you on the NGI Technical Podcast. So we cannot avoid talking about your Rankine lecture, I think. So congratulations again on the wonderful Rankine lecture. So I believe everybody has enjoyed your lecture. And you shared fascinating insight on how emerging technologies and observational methods could help to ensure the safety and cost effectiveness of infrastructure assets. So what initially inspired you this approach?
Yeah, it's been taking some years to figure that out.
Yeah.
But it came by talking to my colleagues and working on projects. And really, we have benefit from the infrastructure we built over the past 100 years. However, we realized that demands continuously change because of the societal changes and environment and all these things. And there are significant engineering efforts underway to renew it all the time. So sometimes these efforts can be very costly and placing a financial burden to the public, both time and the efforts, who ultimately have to pay for it as a public, I think, for infrastructure. So this realization inspired me to explore the concept of adaptive infrastructure, which requires a sort of deeper understanding of how our existing infrastructure, whatever we're going to build, really truly performs. So this is where the motivation came.
Yeah, I think we are facing a challenge about aging infrastructures everywhere in the world. In your lecture, you touched on a couple of applications, case studies, such as pipelines, tunneling, piles. Could you share with us some other potential applications?
Yes, so we've been trying different things to see where the value that some of the sensing technology we work on can help to realize that adaptive infrastructure concept. So we've been working on like levees, embankments, retaining walls, including ground anchors and soil nails, pavements, natural human-made slopes, mooring lines, very deep wells. So we've been trying many of the geotechnical related structure, but we also have a project on recording whale singing along the coast of California in relation to offshore wind energy project. So we're trying different things.
Yeah, you have covered almost all geotechnical aspects.
But I think there are a lot of opportunities.
Yeah, sure. You have been also a pioneer in constitutive modeling geotechnics from the micro to macro scale, and also large deformation analysis using, for example, material point method. So how this change has this method changed the field? What do you think of those aspects?
Yes, I believe we now have a better understanding of how soil particles interact with each other at the micro scale, which help us to understand their macroscopic behavior. So what does friction angle mean? So what does stiffness mean? So this insight has deepened understanding the role of especially the soil fabric and the changes in its mechanical properties. So I think we have gained greater appreciation of the so-called critical state soil mechanics and its application to how to normalize complex soil behavior. However, it also highlights a certain limitation of these classical critical state-based soil mechanics, such as like camp clays or North sand, because the role of the fabric that we have in our soils. For example, it is evident in the like softening and stability behavior of sensitive clays that you have in Norway. As well as sort of a static and quasi-steady state behaviors observed in loose to loosium medium sand. And these are all related to changes in soil fabric, and we sort of understand that. So I think that's where we are moving, and I think that particular appreciation of soil fabric is changing the field at the moment.
Yeah, we noticed that from your lecture as well. You have this nice and fascinating combination of finite element modeling and fiber optic sensing. So are there any particular projects where this method or the combination of this method made a critical difference in outcomes?
Yes, it's related to large deformation modeling. I became interested in modeling large deformation simulation because the conventional slope stability analysis does not provide information about the timing of potential failures. So we've been exploring, once you do these sort of conventional slope stability analysis, use that outcomes to go to large deformation analysis and figure out to understand whether the failure will be brittle and catastrophic or more ductile and gradual. And this is sort of well-used concept in building design against large explosion. And however, geotechnical engineering can incorporating such framework a little bit more in terms of brittle and catastrophic versus ductile and gradual. And I think this is crucial for developing related to monitoring strategies. Are you prepared for sudden changes, or you watch things creeping, and preparing for effective sort of mitigation plans or evacuation plans. So it links to sort of social science aspects of how people tell them to prepare for evacuation. So that's where I think I see some value of moving more classical geotechnical engineering to try with these large deformation modeling to see how we can link to public awareness and emergency preparedness.
Yeah, it's quite beneficial for the public, the whole society. You have had a remarkable career spanning decades. So what were the most important developments and innovations in geotechnics throughout your career?
All right. I think every development is important for my point of view. And what geotechnics excel is at is exploring societal issues, which include like environmental geotechnics, energy geotechnics, deep geomechanics, and more like that. And I think for me, it is important that new generation leaders emerging through these developments and keeping the discipline exciting. So I don't have a favorite one, but I see this progressively always changing to meet the societal needs is something that I feel that geotechnics in general has been very successful. And I hope this will continue.
Yeah. I believe we still have a very bright future.
Yes.
I think most of you know you have played an important role in the establishment of the Center for Smart Infrastructure in both University of Cambridge and UC Berkeley. Could you say something about the mission of both centers and what's the difference between these two centers?
Yes. So while I was at Cambridge, the Center for Smart Infrastructure and Construction, so that's why we call it CSIC.
CSIC.
Yeah, focused on monitoring construction activities, thinking about performance-based design, and can we do better in design, and then understand the actual performance of what we build. And it sort of coincided with many large infrastructure renewal projects that was happening in London at that time, including Crossrail projects. On the other hand, the Center for Smart Infrastructure at Berkeley, it doesn't have that construction, but really focus on infrastructure resilience and really combining data to performance throughout the life of the asset, looking at system level thinking of our asset, what kind of service we can provide, and what are the resilience that we can provide as an engineer from the asset point of view. And it's not really just for natural hazard, it can be for other issues. But having those two framework of sort of a service level, sort of a asset, sort of a service providing versus the asset management, how they can combine together to provide resilience against climate change or natural hazards. So the Berkeley Center is a little bit more focused on that.
Do you say there's any difference in terms of data volume? I mean, with all these new techniques, we start to acquire more and more data, I think.
Yes. Yeah. So I see that more. And obviously, if you start from construction, what you want to do is to keep that data. So how do we make sure that we keep that data? The challenge that we have for the resilience is that we have the data, but then maybe the data only comes from 1990s. So only the past 20 years, 30 years, but then many of the assets that we want to look after originated before that. So we have this particular issue of, we call it left truncated problem, that we don't have a data earlier. So how do we extrapolate the information that we have to go backwards in history and then look forward to the future? And that's where the really interesting part of the data analytics. So we do have data, but the data may be limited in a certain time frame. And then we start to explore how to go backwards, but forward. So that is the interesting challenge that we have at the moment.
I fully agree. So what motivated you to Cambridge and then brought you back to UC Berkeley? I know I have heard some story from you.
Right. Well, like NGI, I think both institutions have great people to work with. And I think I'm a little bit more not a sort of individual person just working on one thing. I tend to work on different things with many different people because I get a lot of inspiration by from working with the others. So, and then at Cambridge, actually, because I was educated in Japan and the US, Cambridge brought a different soil mechanics perspective that I didn't have before. So that really expanded my horizon in terms of geotechnical engineering. But then after working in Cambridge, at Cambridge for 20 years or so, going back to Berkeley, now giving me different perspectives or aspects dealing with natural disasters. So I'm exploring many things every day.
Yeah.
And I think both institutions have been giving me all these interesting sort of insights but also at the same time challenges.
Yeah, that's quite inspiring for next generation as well. So every day we should start exploring new things. So what we have been talking about sensing technologies and data science, and personally we have exchanged a lot of experience in terms of artificial intelligence, machine learning. So how do you see the role of geotechnical engineers evolving in the coming decades?
Yeah, I see the importance of the understanding of geotechnical mechanisms deeper. From the data, what do you see? What kind of mechanism you can extract so you can do the right thing and make a right decision? And to do so, we may need to change our teaching in geotechnical engineering, not only show how to design using classical design methods or numerical methods, but really showing how it really behaves, how you think it's going to behave, and then trying to what to look for, so that you have this particular, you can make a better, good judgment of what's going on. And in order to do that, you need to understand the mechanics, how things behave, and then where you want to monitor, and then make a right decision. Because ultimately, we hope that machine learning or AI won't make decisions. We are the one making decisions. Of course, they can judge what's happening and help us doing some judgment of the behavior. But ultimately, I hope that we still make a good decision. And that good decision comes from us understanding what's going on.
Yeah, absolutely. I cannot agree more. I think personally, I also think we should incorporate our expert judgment into our geotechnical designs. So I think since you moved to UC Berkeley, you have been working with resilience and also sustainability development. So how does a smart infrastructure system contribute to the sustainable development and environmental protection, and maybe from the perspective like saving material and doing a good job for the society, for the environmental issues? So what do you think about all these issues?
Yes. So my hope is that if we can have more data, we can make our infrastructure more cost effective in terms of creating it or maintaining it or renewing it. And that can lead to less materials, as you say, or reuse of the material. And then use the money that for savings, we can use that for environmental protection. And therefore, we are using our resources not only sort of material side, but also money-wise, effective. And in order to do so, we need to understand the actual performance and figure out where to make improvements. And that's where our data can help us. And then we make the right decisions so that we can have this sustainability and environmental protection.
Yeah, this sounds pretty promising. I mean, in some part of the world, I mean, we don't have that many construction jobs. But for the maintenance and all this resilience of aging infrastructures, I think we still have a lot of work to do for geotechnical engineers. And what have been the most significant advancement in geotechnics over the past decades, in your opinion? I mean, we have a lot of innovations, we have a lot of developments. So in your opinion, what's the most significant advancement in our geotechnics?
Yeah, for me, it's about data-driven understanding of complex geotechnical behavior and trying to figure out what's really going on. And I see that in particle mechanics. Why do macroscopically soil behaves in this way, so that you can do better in their design and become more efficient in the way we do geotechnical construction and maintenance. And at the same time, we see this AI and all these coming perhaps to help us to sort out bigger amount of data. And I think that's where, again, we can do a better job in providing good value to the society. And I think ultimately for me, it's about gathering the data, real data sets.
Sure. Yeah, well, you know, what inspired me a lot from your lecture was that you mentioned a couple of previous Rankine lectures from Peck, from Mark Randolph, from Robert Mayer, and we see this a lot of these conventional approaches, but you introduce the new data-driven machine learning into all these aspects. I mean, we could have our traditional geotechnical engineering with all these new technologies.
Yes. So when we say traditional geotechnical engineering, of course, it became traditional because we understood the mechanism of how geotechnical structure behave, and then became a traditional in a sense of became codified, and then you design based on that mechanisms. So I think really appreciating going back to that mechanism. So don't use the design code like a cookbook. But see what is the mechanism, and then by seeing the data, is that the right mechanism that you used when you're sort of designing it? And then if it's so, then you're good. But if it's not, you can make judgment and then decision to how to move forward. So I think trying to understand the reality and then trying to go back to the mechanism used by your design, is that the right thing? And then that will give if it's yes, then you learn. And if it's no, you learn again.
Absolutely.
So that particular process of learning is so important that will move forward as a geotechnical engineering to do a better job in next one. So that's where I want to, even in traditional geotechnics, let's try to go back to where that came from, and then confirm that with the data.
Absolutely. Are there any research areas where you feel geotechnical engineering still have major gaps, or we have to address?
Right. I don't think. I think the gaps I see is more, again, trying to codify things too much, and then assume the variability of certain things, like engineering properties and uncertainty analysis of that. But then we all know that when you go to real construction, there are a lot of construction-related uncertainties.
Sure.
And these are things that sometimes we miss, but then dictates the behavior of our geotechnical structures. So the gap may be more appreciating other parts of uncertainties in geotechnical engineering rather than not just focusing on the engineering properties like strength. And that's what our profession is about, is to how to deal with the ground heterogeneity. But then I just want to say there are other uncertainties that we need to think about. Even models, you can pick different models. And that's another uncertainty because every model has assumption, and this assumption creates uncertainty whether it's true or not. So just appreciating the other parts. And if you have more data, I think you get better understanding of the appreciation of the other parts of the uncertainties. So I'm not saying it's a gap. It's not a gap, but then I think there are opportunities to look into that.
As geotechnical engineers, we have made a lot of efforts to interpret soil properties. I notice your green, orange, and red lines. So we interpret all these undrained shear stress behaviors. Absolutely, we have uncertainties in our models as well. So we develop our finite element model. We develop our empirical models. But we do appreciate, I think, the observation no method. As you mentioned, from construction, you need to utilize all this data to reflect some limitations we have.
Yes. And then I was talking to your colleague yesterday about, well, of course, we're trying to categorize. So we say that undrained, and then we say drained, or clay soil, or sandy soil, because it makes our thinking conceptualize better. But then at the same time, the reality is partially drained sometimes, or silty soils. So I think that is something that we need to think about. What are the uncertainties, not on the soil properties, but then the soil fluid interaction in drain or undrained. So that's where the model uncertainty comes, because you use Tresca model for undrained and then effective stress model for the drain, but then the reality may be somewhere in between sometimes.
We always have the issue about partial drainage.
Yes. So
I know you have a very busy calendar. We have kept you busy all the time at NGI. So one last question. Do you have advice for future generations of geotechnical engineers?
Yeah, I just want to say, please explore new areas of research and development. And it takes time to being recognized. So be patient sometimes. But I just want to say that every resources or materials that you see in front of you, cups or any plastic materials, they come from the ground.
Yeah, sure.
Unless we go to the space, but we haven't done that yet. So I think we should be proud that we are working the fundamentals of the earth. And this is so interesting area for me. And so just explore new areas, because everything that we have in front of us comes from the earth.
Absolutely. Thank you very much, Kenichi, for this personal and inspiring podcast talk. It was great to have you as a guest. I believe they will make the best out of this technical podcast. Thank you very much.
Thank you so much. Thanks, everyone.